Hey, full stack devs. Ever felt like your brain is a tangled mess of buzzwords? We've all been there. Concepts like concurrency and parallelism, or monoliths and microservices, get thrown around so much they start to lose their meaning. But understanding these core ideas is what separates a good developer from a great one. Let's untangle these back-end concepts and level up your knowledge. First up, a classic mix-up: API gateway versus load balancer. Think of an API gateway as the smart receptionist for your microservices. It's the single point of entry for all incoming client requests. It handles things like authentication, rate limiting, and routing, making sure the right request gets to the right service. A load balancer, on the other hand, is the traffic manager on a busy highway. Its primary job is to distribute network traffic efficiently across multiple servers to prevent anyone from becoming overloaded. This ensures high availability and reliability for your application, no matter the traffic. Next, a fundamental concept every dev needs to know: authentication versus authorization. Authentication is the process of verifying who you are. It's like showing your ID at the entrance of a building. Common methods include passwords, multi-factor authentication, or biometric scans. The goal is simply to confirm your identity. Authorization, on the other hand, is about what you are allowed to do once inside. This is the security guard checking your badge to see which floors you have access to. It's about granting permissions. So authentication verifies identity, and authorization grants access and permissions. These terms are often used interchangeably, but they describe very different things. Concurrency is about managing multiple tasks at once. It's like a chef multitasking by preparing a salad while waiting for water to boil. The tasks are independent and can be interleaved. You might have a single core, but the OS makes it seem like multiple tasks are running. Parallelism, on the other hand, is about running multiple tasks simultaneously on multiple cores. This is like having two chefs, each cooking a different meal at the same time on separate stoves. Parallelism requires multiple processors or cores, while concurrency can be achieved on a single core. These two are often used interchangeably, but they measure different things. Scalability is a system's ability to handle an increased load. Think of it as adding more lanes to a highway to accommodate more cars. A scalable system can grow to handle more users, more data, or more transactions. Performance is about how fast a system responds under a given load. This is about how fast the cars are traveling on the highway. It's measured in things like latency, throughput, and response time. You can have a high-performance system that isn't scalable, and a scalable system that has poor performance. The goal is to have both. This one is a great interview question. Framework versus library. A framework controls the flow of your application. It provides a skeleton that you fill in, giving you a strong opinion on how things should be done. You write your code within the framework structure. It's often referred to as inversion of control. The framework calls you. A library, however, is a collection of pre-written functions you can call whenever you need them. You are in full control of the application's flow. You decide when and how to use the library's functions. So, a framework is the house you build in, and a library is a tool you use to build your house. Let's dive into databases with relational versus non-relational. A relational database is like a spreadsheet with a rigid structure. It uses structured data with fixed schemas and tables. It's great for applications that need strong data integrity and have well-defined relationships between data, like financial systems. A non-relational, or NoSQL, database is far more flexible. It's like a flexible filing cabinet that can hold anything. It uses a dynamic schema and is designed for large-scale data and high-speed operations. You can store data as documents, key-value pairs, or graphs. The choice depends on your data structure and how you need to access it. Let's get into the nitty-gritty of how programs run with process versus thread. A process is an independent execution unit with its own memory space. It's a running program like a browser or a video game. Each process has its own resources, which makes them robust but also means more overhead to create and manage. A thread is a lightweight unit of a process. It shares the same memory space as other threads in that process. Think of threads as multiple workers inside a single factory. They can work on different tasks, but they all have access to the same shared tools and materials. Because they share memory, threads are faster to create and switch between than processes. This is a common source of confusion for developers: caching versus memoization. Caching is a general-purpose storage of expensive results. It's about storing data that is slow to retrieve or compute, like a database query result. Caches can be implemented at different levels, like in memory, on a server, or in a CDN. It's often for external data. Memoization is a specific form of caching applied to function calls and their results. It stores the result of a function call based on its arguments. If the function is called again with the same arguments, it returns the cached result instead of recomputing it. So, caching is a broad strategy for storing data, while memoization is a specific optimization technique for function results. This is a major architectural decision for any system: microservices versus monolith. A monolith is a single, unified application where all logic is bundled together. It's like a single engine plane. All parts are tightly coupled. This can be simpler to develop initially and deploy, but becomes difficult to scale and maintain as the code base grows. Microservices are small, independent, deployable services that communicate with each other. This is like a fleet of small, specialized planes. Each service does one thing, and does it well. This architecture offers better scalability, resilience, and independent deployment, but comes with increased complexity in management and communication. In error handling, two philosophies dominate: fail fast versus fail safe. A fail fast approach means an application or component fails immediately and loudly when an error occurs. This is great for debugging and finding issues early in development, but can be problematic in production if not handled properly. A fail-safe system, on the other hand, recovers gracefully from failure. It might log the error and try to continue or switch to a degraded state to prevent a full crash. Think of a fail-fast system as a light that goes out entirely if the bulb is broken, while a fail-safe system might just dim or flicker, but stay on. This is a crucial concept for building robust APIs: idempotent operations. An operation is idempotent if performing it multiple times produces the exact same result as performing it once. A good example is a put request to update a resource. Updating the same resource with the same data multiple times has the same final state. This is critical for scenarios where network issues might cause a request to be sent twice, like in payment processing. If a payment API isn't idempotent, a user might be charged twice for the same transaction. That's a huge problem. Designing APIs to be idempotent is a best practice for safe and reliable systems. This is a core principle of object-oriented design: composition versus inheritance. Inheritance is a hierarchical way to reuse code. You create an ISA relationship, where a child class inherits properties and behaviors from a parent class. It's often less flexible because you are tied to a rigid class hierarchy. Composition, on the other hand, is about building new objects by composing them with other objects. This creates a has-a relationship. An object has a behavior from another object rather than inheriting it. This approach favors combining behaviors and is generally more flexible and adaptable. When your system needs to handle more load, you have two main options: horizontal versus vertical scaling. Vertical scaling means adding more power to a single machine. Think of it as upgrading a server with a faster CPU, more RAM, or a larger disk. It's simple, but you're limited by the physical limits of a single machine. Horizontal scaling means adding more machines to your system. This is done by adding more servers to a network and distributing the load with a load balancer. This is generally a more scalable and resilient approach. If one server fails, the others can pick up the slack. It's often a more complex setup, but it's the key to building truly scalable systems. These are two ways to design distributed systems. Let's clarify event-driven versus message-driven. Event-driven architecture is a decentralized model where components react to state changes or events. A component publishes an event, and other components can subscribe to it. The publisher has no knowledge of the subscribers. A message-driven system is a more centralized model where components communicate explicitly via messages. The sender sends a message to a specific receiver, expecting a response. Think of it as a formal conversation. The key difference is that events are a broadcast of a state change, while messages are explicit commands for a specific action. Finally, two terms that are absolutely vital for security: encryption versus hashing. Encryption is a two-way process. It takes plaintext and turns it into ciphertext using a key, and it can be decrypted back to the original data. This is used for sensitive data that needs to be transmitted securely and then read, like a credit card number. Hashing, on the other hand, is a one-way process. It takes an input and produces a fixed-size string of characters, called a hash. You cannot reverse a hash to get the original data back. This is used for integrity checks and for storing passwords securely. So, encryption is for protecting data in transit, while hashing is for protecting data at rest without ever needing the original value. And there you have it, 15 backend concepts that are often misunderstood. By knowing the difference between a load balancer and an API gateway, or concurrency and parallelism, you're not just memorizing buzzwords, you're building a stronger foundation for a career in software engineering. The more you can articulate these core concepts, the more confident you'll be in interviews, and more importantly, in your day-to-day development work. If this video helped you untangle a few concepts, hit that like button, and subscribe for more deep dives into the world of full-stack development. And I'd love to know, what other backend concepts do you find confusing? Let me know in the comments below. Keep on coding, and I'll see you in the next video.